Switch on the camera, all of you, but only 9 people have joined. So Richa is back to the normal position, normal room. अरे कौन है? प्रसाद वसंत, कैमरा ऑन करो. But where is few people? Moria, are you there? Moria Manish, yeah, he is there. Moria Manish is there. There are a lot of Sai in this class. Sai 1, Sai 2, Sai 3, Sai 4. ये कौन है? Sai Krishna. बराबर, lot of Sai. So 14. चलो, so we can start. 14. No, Sabba, you don't smile. Huh? Don't smile. It is nice to see you people smiling. You know why? अरे वो क्या कर रहा भाई? प्रशांत, क्या गड़बड़ है स्विच प्लग पॉइंट में?
Sir, actually laptop has low charging.
अभी याद आया?
Sorry, sir.
अभी याद आया. Anyway, so let me have a little bit of discussion with you. And it's nice to see you people smiling because आज का मैथमेटिक्स थोड़ा भयंकर मैथमेटिक्स होंगे. आज और नेक्स्ट क्लास का मैथमेटिक्स कुछ भयंकर होंगे. So be ready for that, and I won't mind if you people can simultaneously have lunch also. Shrabha, breakfast?
Yes, sir.
Good. क्या लिया?
Sir, I don't
Idli?
know the name in Hindi.
Huh?
I don't know the name of it in Hindi.
You don't know what you have taken in your breakfast?
I know it, but I don't know the name of it in English or Hindi.
In Telugu, what is it?
Sir, Semya Upma.
Acha, I could not understand it. Anyway, it doesn't matter. It doesn't matter. But sometimes don't get offended if I talk about your breakfast menu or lunch menu. Don't get offended. Fine. The reason is simple. Generally, I don't have my own breakfast till this time. So just listening that you have had your breakfast, it gives me enough to go ahead for another 1 hour. Okay? So Nandana is smiling. Nandana, in Telugu, what is the breakfast that you have taken today?
Idli, sir.
So there is a Hindi, there is a English for that. Fine. Good. So all of you, please listen. I mean, we can go to the PPT directly, but before that, let me. You have any question or not? Because we have just entered in a very difficult chapter, that is transient excitation. Okay, and in transient excitation, what we are trying to do, please listen this carefully. We are not interested how the response looks like, because we know that this response will finally die out. Because it's a transient excitation. So this response will finally die out. We know that. So in transient excitation, we are not interested to study how the response looks like. So what do we study in the response? We study, or we try to find out what is the maximum value it will reach. So before that maximum value, how it arrived at that maximum value, or after the maximum value, what it does, we don't pay any concern to that. Our only concern is what is going to be the maximum value, because from that maximum value we can calculate maximum stress and we can design it against tensile failure or ultimate failure. We don't design it against endurance limit or fatigue strength. I have already mentioned it in the last class. Under transient excitation, the failure is not fatigue failure. But in case of harmonic excitation, failure is fatigue failure. This is very important. So under transient excitation, failure is not fatigue failure. Failure is tensile failure or ultimate failure. Okay? So in tensile failure or ultimate failure, we only bother about what is the maximum stress or what is the maximum vibration displacement. So if we plot that maximum displacement against the ratio T by TD or omega by omega n, we get a graph. That graph we have already mentioned is known as response spectrum. I have already mentioned the graph is response spectrum. And in last 2-3 lectures, we have discussed how to get that graph for different kind of transient excitation. We have taken up a unit step function, we have taken up pulse, we have taken up half sine curve, and maybe I have not mathematically solved, but I have introduced triangular pulse curve, so many things we have discussed. Today we will discuss perhaps the most important transient excitation, and that is earthquake. But before we come to earthquake, little bit of mathematics you have to understand, then we'll come to earthquake. Among all the transient excitation, 2 types of transient excitations has challenged engineers. One is earthquake, the other one is this wind excitation. You can call it hurricane, you can call it typhoon. These names are different depending on different geographical locations, or you can call it funny. यहाँ पे भाईजैग से कौन है? नंदना, you are from भाईजैग?
Yes, sir.
तो भाईजैग की 2-3 बातें कर सकता हूँ.
Yes, sir.
Have you been to Vizag? Have you landed in Vizag by air?
No, sir.
No, sir. ठीक है. So can you see a aeroplane in Vizag city?
Yes, sir. I see those landings right there.
Okay. Can you tell me what is, for others also it is an important discussion I am talking about. You might not have, but other people must have, anybody who has visited Vizag by air? कौन है, क्या नाम है? So you have visited from which place? Correct. So it takes hardly 1 hour 15 minutes, not more than that. So can Sai Sagar, you tell me why Vizag airport is very crucial airport? There are 2 airports which are very crucial. One is Vizag, the other one is Mangalore. Okay. Vizag में क्या why I'm calling it crucial? I know Sai Sagar never paid attention when the plane was landing. He was looking at the air hostess. Sai Sagar never paid attention how the plane was landing. Am I correct? Anyway, it doesn't matter. See, in Vizag, please remember what is the challenging thing in Vizag airport is, one side it is hill. Nandana will correct me if I am saying anything wrong. One side there is hill, the other side there is sea.
Yes, sir.
So once the aircraft crosses the hill, immediately it has to start descending. अगर पायलट 2 सेकंड के लिए भी सो गया, plane will land in sea. So you need very expert pilot there to land in Vizag airport. So many a times plane क्या करते हैं, after it crosses the hill, it doesn't try to land. ठीक है, it doesn't try to land. वो बोलता है चलने दो. So they go to the sea, then come back. Then turn. Am I correct, Nandana?
Yes,
You will
sir.
see
They
many
take
a times. So in Vizag you will see many a times planes are taking a turn. Oh, पहले they over travel, and then go to the sea, take a turn, because from sea they can land with not that much of sharp descent. But after the hill, if they try to land, so they have to land very high gradient. It's very difficult, very so. But why I talked about Vizag aircraft? हम तो vibration की बात कर रहे थे. Oh, okay, fine. So this funny came in Vizag. That's why I connected Vizag. So depending on whether I am in India or I am in, you know why these hurricanes, they are given different name? Sometimes funny, sometimes Ida, sometimes Nandana. ऐसा क्यों नाम देता है नंदना? 2009, I think that was Hudhud. क्या था Hudhud? क्या था नाम?
Hudhud, sir. 2015 में.
15 नहीं होगा और आगे होगा. Anyway, तो अभी जो है उसका नाम फनी क्यों हुआ? उसको भी Hudhud 2, Hudhud 3, थर्ड सेमेस्टर, फोर्थ सेमेस्टर ऐसा क्यों नहीं दिया? Because in Vizag, this hurricane is very common. Am I correct? Almost every year something comes up. Can anybody answer it? Why the names are different every time? Richa? बोलेगा मैं तो नागपुर में हूँ, मुझे वाइजैक से क्या लेना देना है ना? A typical Indian student's answer. Why should I bother about what's happening in Vizag? Why these cyclones that keeps coming to India almost every year, they have different names and very peculiar names sometimes. At least funny we can understand. Sometimes they will come this time this is funny, other times it will be funny. Any idea? You should have your general knowledge also. कोई बता सकता?
Sir, they are named for identification purposes by many countries.
Correct. This is the correct answer. There are 7 countries. Pakistan, Sri Lanka, Bangladesh, India, and maybe Indonesia also. 7 countries. Depending on the proximity of original starting, names are given. ऐसा नहीं कि इंडिया में आ रहा है इसीलिए नाम इंडियन होगा, ऐसा नहीं है. डिपेंडिंग ऑन द लोकेशन जहां से चालू होता है उसका प्रॉक्सिमिटी, और अब मे बी एवरी टाइम वन पर्टिकुलर कंट्री गेट्स ए चांस टू गिव अ नेम. ठीक है. एनीवे, सो लेट मी कम बैक टू साइक्लोन. सो दिस साइक्लोन और हरिकेन और टाइफून, they are transient excitation. However, much serious transient excitation is earthquake. Fine. Much more, the damage that occurs in earthquake is much more devastating than these cyclones or hurricanes or typhoons. So we will talk about earthquake little later, maybe after 20 minutes. Before that, some amount of mathematics you have to digest. So let's go, take out your camera, let's go to the mathematical side. अरे उसको मैं ओपन नहीं किया. I hope you can see it. This is written in red ink, so I'll enlarge it so that it is visible properly. Fine. So just read it. Just read it. I hope you can understand yourself, but I'll also explain. Just look at it and try to understand it. I'm repeating what I have discussed in the previous class, but something more this time. This is impulse excitation. This is impulse excitation, but what I have done, impulse excitation, but I have shifted it tau seconds ahead of 0. So this impulse excitation is not occurring at t is equal to 0. It is occurring little later. How much later? Tau. So if an impulse excitation occurs little later, it is not written as delta t. It is written as delta t minus tau. So whenever this symbol comes up in front of me, delta means I'm talking about impulse excitation, and t minus tau means this impulse excitation is occurring at the instant tau, not at t is equal to 0. So accordingly, the response, of course, what is the difference between A into delta t minus tau and delta t minus tau? Delta t minus tau is unit impulse excitation. The area under the graph will be unity. But in real life cases, this area is impulse, and it may not be always unity. It can be, instead of unity, it can be 2, 3, 4, 5, anything. So if the area is not unity, then the force is represented by value of the area multiplied by delta t minus tau. So don't get confused between this symbol and this symbol. If the symbol is written with a coefficient capital A, इसका मतलब है कि impulse का जो area है, that area equals to capital A. If it is unit impulse, this area will be 1. I will not write 1. I will only write delta t minus tau. But if I write A into delta t minus tau, it means the area is not unity. So it is impulse excitation, but it is not unit impulse excitation. Any confusion? Let me know. The difference between this and this. In both the case, we are talking about impulse excitation. In both the case, we are talking about impulse excitation taking place after a delay of tau second, not at t is equal to 0, after a delay of tau second. However, in this case, the area under the excitation graph is unity. In this case, the area under the excitation graph is A. That is the only difference. So this is unit impulse. This is not unit impulse. That is the only difference. Both are impulse excitation. Both. Corresponding response, we have already mentioned. When we have delta t, response is ht. So because my excitation is delayed by t minus tau, my response will also begin after t minus tau. So the response is h into t minus tau. What is h? H I mentioned in the last class, impulse response function. H is the response when excitation is impulse excitation. So for delta, because it is t minus tau, h also will be t minus tau. If it is multiplied by A, response also will be multiplied by A. So this is the response under a general impulse excitation. Try to digest it. This is the value of the response for a general impulse excitation. Why I am calling general? Because this excitation area magnitude need not be 1. It can be anything. This impulse excitation should not take place exactly at origin. It can take place anywhere. So this is the formula for response for a general impulse excitation. What do I mean by general impulse excitation? Its occurrence can take place any time later than t is equal to 0, and its area value can be anything given by A. Any problem? किसी को कुछ क्वेश्चन है, सवाल समझ में नहीं आ रहा तो पूछो. So if I have a general impulse excitation, then my response will be given by this formula. But remember, a formula में एक causality embedded है. What is that embedded causality? t minus tau indicates that my response will start building up only after tau. So A zone mein response was 0 because excitation did not come. So excitation starts building up only after t is equal to tau. Please remember, h is such that t less than tau, h is 0. So ht minus tau is h after t is equal to tau. So impulse response exists only after the impulse has taken place. Impulse response does not exist before that. So this is called causality principle. Response is caused by excitation. So response cannot happen before the cause. Cause effect. Effect cannot occur before the cause. Effect always happens after the cause. Okay? So this xt exists. Let me repeat again. This xt exists only for t greater than tau. It doesn't exist or it is 0 if t is less than tau. I have not written it, but it is embedded. It means this t exists only after t greater than tau. Okay. So for a general excitation, if this is the response and if there are two impulse excitation, one occurring at tau 1, area is A1, second one occurring at tau 2, area is A2. What will be response at a future time t? It will be A1h t minus tau 1 plus A2h t minus tau 2. Do you agree? Do you agree? I have not mentioned one thing. What is that I have not mentioned? Here, I should have mentioned. What is that I have not mentioned? First of all, do you accept it from this? From this, can I write this? Because I am skipping something. What is that I am skipping? I should. I cannot skip. I cannot skip. But can you guess what are the two lines? What are the two lines which I must mention here? Otherwise, I cannot say that this answer is correct. What are those two lines? अरे थोड़ा दिमाग लगाने का कोशिश करो, चुपचाप बैठे रहोगे तो कुछ नहीं होगा.
Response will superimpose after tau 2.
Repeat again. What did you say?
Responses will superimpose after tau 2.
Okay. Anyone else? And keep thinking. If you try to remain silent, then perhaps you may not pass this subject. Subject इतना आसान नहीं है. What are the two things I should mention? And I will mention also, but I thought that rather you people can point me out. Can I superimpose both the responses always? No, what is this? What is this? This is response at t because of this excitation. And this one is response at t because of this excitation. Can I superimpose? Can I add? Always. Is there any condition that I cannot add them? No, this is a famous principle. We call it principle of superposition. So principle of superposition says that effect for two different causes can be superimposed or added together, provided cause effect relationship is linear. Provided cause effect relationship is linear. So if our system is governed by linear differential equation, then we can say yes, this superposition is valid. But if our system, or that is equilibrium equation, is nonlinear, we have seen, we have from Lagrange equation, we have already seen, sometimes our differential equation is nonlinear. But most of the times, the differential equation that we have used in single degree of freedom, it is linear. mx double dot plus cx dot plus kx, it is a linear differential equation. So as long as my differential equation is linear, I can superimpose. So that is statement number 1. Statement number 2, which I haven't mentioned, this formula is valid for t greater than both tau 1 and tau 2. This formula is valid for t greater than both tau 1 and tau 2. If t is somewhere here, second term will not appear. Only first term will remain. So this superimposition I am going for an instant time t which is greater than both t1 and t2. So if we accept this superposition, now what I am doing? Now I am taking an excitation who is not two impulse excitation, who is a continuous excitation. However, it is varying in a peculiar manner. It is not a sine curve. It is not a rectangular pulse. It is an arbitrary variation. Okay? Which means this f is given by, if this axis is tau, f is given by small f tau. So for every value of tau, the value of f tau is the y value. And it is changing. It is changing. So what do I do is, I cut out a small strip, and I say that this is one impulse standing at tau. And what is the area of the impulse? F tau into d tau. If f tau is the height, f tau into d tau is the area of the impulse. So what will be corresponding response at time t? Area multiplied by h into t minus tau. Now, there will be infinitely many such strips. So this summation is not summation of one term or two term. This summation is an infinite sum. And as you know, infinite sum is represented by integration. So this infinite sum is converted into integration 0 to t f tau h into t minus tau d tau को हम आखिरी में लिख रहे हैं. So this is my overall response at t's instant t. Because of a force which varies in an arbitrary manner, then I can calculate the response at some instant t by this integral formula. And this is a famous formula known as Duhamel integral or convolution integral. ठीक है, ये फॉर्मूला को लिखो, अपना नोटबुक में फॉर्मूला को लिखो, और आई विल गिव यू द पीपीटी. थोड़ी देर चेहरा देखो, और कुछ डाउट है तो मुझे बताओ, कुछ समझ में नहीं आया तो मुझे बताओ. वी आर यूजिंग प्रिंसिपल ऑफ सुपरपोजिशन. So this Duhamel integral is valid for linear differential equation, linear system. It is not valid for nonlinear system. So if you have understood it, look at this f tau. इसमें देखो, I'm expecting some question showing that you are going to become an engineer from VNIT, of course, from VNIT. You are not asking anything. Do you think this formula raises some question in your mind?
Sir, why is there h bracket t minus tau here?
Why?
Yes.
I'm converting this summation into integral. That's all.
Sir, that one's a t minus tau.
ये तो शुरू से ही आ रहा है. अच्छा, why it is t minus tau? This is
Okay.
t.
This term is why is there because without it we can also integrate.
Without tau, you can integrate. No, who is varying here? See, this is one impulse. Next, I take another impulse. So who is varying? Tau is varying. T is not varying. Tau is varying. T is a given instant. T may be 4 seconds. So T remains 4 seconds. Tau varies from 0 to 4 seconds. T is the instant when I want to find out my response. उसके बाद T को भी हम वैरी कराएंगे. ऐसा नहीं कि T 4 सेकंड ही रख देंगे. But first we fix T at a particular value. Maybe T is equal to 4 seconds. And then we vary tau. तब जाके मुझे response at T is equal to 4 seconds मिलेगा. Then I vary T. I make T is equal to 5 seconds. Again I vary tau. So for every value of T, I vary tau. So d tau enters into the integration for a given T. For a given T, d tau is the integrand with respect to what we have to carry out the integration. So for every T, T also varies. Definitely T also varies. But first we fix T. For a given T, we allow the impulse excitation to happen at every location up to T. So tau varies from 0 to 4 seconds. जब मैं T को 5 सेकंड लेंगे, tau will vary from 0 to 5 seconds. T is equal to 6 seconds, tau will vary from 0 to 6 seconds. So the limits keep on changing. Anyway, I'll still wait for another 2-3 minutes. इसको ठीक से समझो. It is a difficult mathematics. I said right at the beginning that today we are going to discuss slightly difficult mathematics, but not that difficult. और किसी को कुछ पूछना है? Okay, so if you accept this mathematics, but even then, even if you accept this mathematics, this formula raises few questions. वो क्वेश्चन क्या है? फॉर्मूला इज करेक्ट, फॉर्मूला में गड़बड़ नहीं है, वी एक्सेप्ट फॉर्मूला इज करेक्ट, लेकिन दिमाग में कुछ सवाल आता है. देयर आर फ्यू क्वेश्चंस व्हिच कम्स इन आवर माइंड, इन आवर हेड, ब्रेन. You should ask me a question. I mean, if you don't ask, that means you are not thinking deeply. At least then you don't deserve to be in Vienna, NIT. Forget about IIT. You don't deserve to be an NIT student. A formula देख के at least one question should come to your mind. Do you think this formula is helpful? Is going to be helpful to us if I ask you? This formula was formulated by Duhamel, and that is why the name is Duhamel integral. The formula was proposed almost 100 years back, little more than 100 years back. So in the beginning of 20th century, this formula was proposed. But do you think a formula काम का है? Is it going to be helpful to us? Do you think so?
Sir, in practical cases, we don't know the function ft, so maybe not.
किसने बोला? विनीत सोनी. You are almost correct, but I will say we don't know the function. ऐसा नहीं है. Even earthquake we know. Only thing we don't know the earthquake before. लेकिन earthquake हो जाने के बाद we know earthquake. कहाँ से मिलता है? We record earthquake in seismograph. Okay, so we know the earthquake, but not beforehand. We know the earthquake after the earthquake has taken place, provided we measure it. All earthquakes are measured throughout the world now. It's a standard protocol now that earthquakes, and that is why we have seismic station at specific locations where earthquakes are more prone. So we know the excitation. Only thing, we know the excitation after it has taken place, not before. So that is a problem, that we don't know the excitation beforehand. That is one of the problem. But we know the excitation after it has taken place. Even if we know the excitation after it has taken place, still there is a problem. What is the problem? We know the excitation because we have measured it after it has taken place. फिर भी problem है. This integral में फिर भी problem है. वो problem क्या problem है?
We don't know the function analytically.
Correct. This is the correct answer. That this earthquake or cyclone, in them, the force varies in a peculiar manner. We cannot represent them by our known functions. We cannot use sine, cos, e to the power x. Nothing. Because they vary abruptly. I will show how earthquake varies. I mean, this is an arbitrary variation. But फिर भी एक काफी अच्छा वेरिएशन है. हाँ, एक खतरनाक वेरिएशन मैं दिखाऊंगा एक्चुअल एट द एंड मेरे ख्याल से वो होना चाहिए. अरे वो पिक्चर यहाँ पे नहीं है. आई मिस्ड इट. ओके, इट इज देयर इन अनदर पीपीटी. वो दिखाऊंगा. या तो मुझे let me go and show you that, because there will be a continuity of discussion. 1 minute you wait. Let me see which PPT I have that earthquake graph. Yes, हाँ आया है. Share window. Is it visible now? अरे हाँ या ना बोलो.
Oh, yes, sir.
Yes, sir.
So नीचे पढ़ो तो मुझे, then I don't need to speak out everything. This is the earthquake which was measured long time back, of course in US. 1940. This is a famous earthquake, El Centro, California. Anyone who has visited US? I mean, there is nothing wrong if you say no. But still, anyone who has visited US?
Yes.
Okay, no one. किसने?
Richa.
किसको? अरे. Which side you had gone? East Coast or West Coast?
I had gone to Boston. I'm not sure which side.
बॉस्टन कहाँ पे है? बताओ बॉस्टन कहाँ पे है? इट इज नॉट ईस्ट कोस्ट, इट इज नॉट वेस्ट कोस्ट. सेंटर का नीचे में है, साउथ साइड है, क्लोज टू मेक्सिको. ओके, बॉस्टन के पास MIT है, मालूम है कि नहीं?
Yes, sir.
हैव यू बीन टू MIT?
Yes, sir. I've seen the campus.
यू हैव सीन द कैंपस. अच्छा, MIT में नागपुर के स्टूडेंट है. कब गया था?
काफी टाइम हो गया.
अरे बोलो ना कब गया था. 10
6-7 साल पहले.
6-7 साल पहले. तो मुझे बताओ, 6-7 साल पहले यू शुड हैव मेट हिम. सेंटर पॉइंट बॉय, ही इज इन MIT. क्या नाम है?
I don't know, sir.
अरिंदम भट्टाचार्य जी. हाँ, 2013 Oh, he left Center Point in 2011 or 2012. 2012. He left Center Point when he was in class 9. He went to Bangalore for JEE coaching, and his All India rank was 327, but he did not join JEE IIT. He went to MIT. So you could have met him if you were in MIT campus. Anyway, chalo, jane do. Now my question to all the student. ये जगह कौन सा कोस्ट में है? कैलिफोर्निया. Is it towards east side or west side of US? See, you should have general knowledge.
West, sir.
West Coast.
It is near West Coast. Okay, fine. Now, California is very dangerous for earthquake. Let me tell you. Okay, I mean, this is the area where earthquake takes place almost every week. Every week. But nobody bothers. Nobody bothers. So, most of this area is earthquake prone. So, this was one of the most dangerous earthquake that took place in 1940 called El Centro. And this is how the ground motion looked like. Now, can I give it a name of a sine curve or cos curve? Answer is no. We simply cannot. But does it mean this graph which has been recorded is useless? Answer is no. Perhaps we can make use of it, provided we are ready to face little bit of mathematics. But even if we can do something, one question will always remain to us or to every engineer, that I come to know about the excitation once the earthquake has taken place. And now measuring this excitation, I create my conclusion that this building is safe or not. But if the building wasn't safe, it has already got demolished. तो अभी एक इंजीनियर को बताने का कोई मतलब नहीं है, because the damage has taken place. So we'll answer all these questions gradually. But first question still remains that this excitation cannot be represented by a force, by a function. So what do? ये integration हमारे लिए बेकार है. Let me go back to अरे मैंने क्या कर दिया, वो ग्राफ को भी खत्म कर दिया. मेरा दूसरा पीपीटी किधर था? Let me go to that PPT. Yes. Okay. So coming here. So this integration, even if Duhamel is saying that he has done a great job, but this is making no sense, because this is not a function. तो मैं क्या करूंगा फिर? What I should do now? I find that the force is varying in a peculiar manner. It is not an analytical function. तो मैं क्या करूंगा फिर? What should I do? अरे भाई, see, if you say you cannot do anything, तो फिर ट्रेनिंग एंड प्लेसमेंट में जाके बैठने का कोई मतलब नहीं है. कोई मतलब नहीं है. Every company expects you will do something. तो फिर बताना पड़ेगा ना what you will do. If you say I cannot do anything, नौकरी कौन देगा? कोई नहीं देगा. तो बोलो what you can do. You are going to be engineer, so you have to suggest that yes, something can be done. What is that something can be done?
So we can basically we have the measurement of the earthquake. So we basically try to convert it to a function. Basically just
but
go for
do
the
you think we can convert it to function? If you look at that variation, मुश्किल है.
Yes, we can't. So we'll go for just the higher peaks and make like small impulse functions.
नहीं. तुमको इस आंसर से साल भर में 15,000 देंगे तनख्वाह, उससे ज्यादा नहीं देंगे. You have to make your answer much more useful. You people should know. You know. It's not that you don't know, but at least M.Tech students, हम क्या करेंगे? डूहामेल ने हमें एक फॉर्मूला दिया, वो फॉर्मूला 100 साल पहले देके डूहामेल भाग गया. I can't do the integration now because f tau is not an analytical function. So what do? I throw away the formula? Or still I can do something. I can use this formula.
So we can divide the graph into known functions.
अरे वही तो लड़के संभव है क्या? वो जो आर्थ को एक देखा संभव है? Do you think? I mean, can you call it? See, first of all, it is not a periodic function, so you cannot go for Fourier series.
Yes, sir.
But even if it is not Fourier series, can you call it something into cos omega t plus something into sin omega t? But does it look at least that much systematic? No. हाँ बोलो, somebody was trying to say something.
Sir, after calculating the area, we can represent it in our Fourier series.
Fourier series is only for periodic function. That is not periodic. Nothing is varying in a periodic manner. I was expecting answer, I'm slightly sad. We go for numerical integration. And that is why computational methods in engineering was a very, very important subject fifth semester, and students have not picked it up. Without that subject, you simply cannot become an engineer in today's context. So, those who do not know, hearing for the first time, you study yourself. We use numerical integration, either trapezoidal method or Simpson 1/3 method. We use numerical integration. So numerical, we don't look for a function. We only need the numerical value. So because we have measured, we have the numerical value. So L centro was measured with a time gap of 0.02 second. I'll give you that file. मेरे पास वो पूरा डेटा फाइल है. So 0.02 second का गैप में जो वैल्यू है, even if it varied in an arbitrary manner, the values are listed in almost good textbook. Chopra, it is listed. So even I have the value, I can give it to you. So 0.02 gap में जो वैल्यू है वो मेजर किया गया, and it is there with us. So with these discretely measured values, what we can do is we go for numerical integration rather than analytical integration. Last 40 years, engineers have shifted from analytical integration to numerical integration. Last 40 years. Today, we simply don't talk about analytical integration. By integration, we only mean numerical integration. Why? Because practically whatever we need to integrate, most of the times they are not representable using analytical functions, just like earthquake I'm mentioning. So if we simply can't apply any analytical integration knowledge there, we have to go for numerical integration. Next, if those who have done integration, they will agree with me, even if the function is analytic, it may not be easy to integrate it. E to the power minus x square dx. Is it integrable? All functions are not integrable. Do you agree? I think your second semester you might have faced this situation where there are few functions which cannot be integrated, even if they are analytical. E to the power minus x square, I'm saying. Dx, can you integrate? You cannot. This leads to what is known as gamma function. So even if functions are analytic, they may not be integrable. Integration is far more difficult than differentiation. Every function can be differentiated. Derivative we can easily obtain. We have the rule. Every function cannot be integrated. Only few functions can be integrated. We have a vast collection of functions which can never be integrated, even if they are analytic. And if they are not analytic, of course, they cannot be integrated. So this is the reason why engineers today, they don't look into analytical integration anymore. Today they talk about numerical integration. And that is why I'm saying, if you have not taken computational methods of engineering, at least you cannot call yourself an engineer. Okay, today's engineer. So forget it, छोड़ो जाने दो. So this integration can be replaced by numerical integration. If I'm giving you 2-3 days time, you can study it, trapezoidal rule or Simpson 1/3 rule. चलो, now let me go to, आज time हो गया, so let me go to a problem say. So here it is step excitation. So f tau is equal to 1. So this is an analytical function and this is integrable function. So what is step excitation? Mein f tau is what? F tau is 1. It is step excitation. So the value of f tau is always 1. So can we carry out the integration? F tau is 1, so I have not written 1. No, f tau is f0. f0 into 1, so f0. F tau is f0 and this is my h tau. This is my h tau when damping is absent. This is my h tau when damping is absent. And for unit step excitation, f tau is constant at f0. This is f tau, this is h t minus tau, and this is d tau. So this is Duhamel integral. This is Duhamel integral where f tau is f0, h t minus tau is this whole thing. This is d tau. I'm integrating 0 to t. So for unit step excitation, and if damping is absent, Duhamel integration reduces to this. If you agree, carry out the integration and give me the answer. This is integrable function. Don't tell me this cannot be integrated. This is integrable function. Carry out the integration and give me the answer. This will be the last exercise today. I don't want to keep you waiting. लेकिन इसको संभाल के करो, carefully करो. Don't make any mistake. Do this integration and tell me what result you are getting.
F naught upon m omega n square.
फिर ब्रैकेट के अंदर
Only f naught upon m omega n square.
अरे m into omega n square is equal to k. फिर something more और भी कुछ आएगा. That's what I'm saying, that do the integration carefully.
F naught by m omega n square t into 1 minus cos omega n t.
F naught divided by क्या बोला?
M omega n square t.
T आएगा क्या? Will you have t in the denominator?
No, sir.
तो अभी बोला ना? M into omega n square is what?
K.
So this is the answer. And we have already got this answer in the last class. You remember? Unit step excitation ka response we have already calculated. Same answer we are getting. Same answer we are getting. We should not get a different answer. This answer is coming through Duhamel integral. This answer is coming through Duhamel integral. Okay? So we'll discuss Duhamel integral little more in the next class. Earthquake का एक झलक दिखाया. I have not discussed anything for earthquake, but we'll spend one full day, full hour on earthquake. Actually, generally I spend 1 week on earthquake. लेकिन ये बैच मुझे अच्छा नहीं लग रहा. Okay, this particular batch is unable to impress me. So I'll not go deep into earthquake. Although it is a very interesting chapter, but still I will let you know how exactly the damage happens in earthquake, and what a designer, a building designer, a civil designer, what he can do, because he doesn't know what is the problem of earthquake. You know, there are many problems with earthquake. The problem is that I don't know where it will occur. I don't know the place. Second, I don't know the time. And third, I don't know in what way it will vary. So practically, an engineer knows nothing about earthquake. Let me tell you. He doesn't know where it will occur. He doesn't know when it will occur. And third, he doesn't know in what manner it will vary. He knows nothing. But still, he can make a very, very probabilistic scale. He can make a safe design. Probabilistic scale. So probability and statistics comes into it. He can make a safe design. And that is how Japan goes. That is how all buildings in California, they are built. People have not run away from California. Arey, yahan to earthquake hota hai, I will not stay here. No, because engineers have given them confidence that no, I will design a building which will never fail. So how an engineer gives that confidence? There is lot of mathematics. So this is a beautiful science, design against earthquake. I will only expose you for 1 hour or 2 hours, not more than that. I can spend a whole semester on it. This is a beautiful area. And I always say, this is perhaps the most challenging area of an engineer. Why? An engineer knows nothing. And he doesn't know anything, but still he gives confidence to the people. How he can give that confidence? There are lot of innovative ideas. We will discuss something in another 2 days, mainly regarding to earthquake. किसी को कुछ कहना है तो बोलो, last 1 minute. Otherwise, class is over. If you have any doubt, any query, any suggestion, बोलो. ओके, ठीक है. सो क्लास इज ओवर. पहला 3 पेज का पीपीटी अभी मैं 5 मिनट में भेज रहा हूं. ठीक है. विल मीट अगेन फ्राइडे. चलो, हो गया. यू कैन लीव.